Alright, so we'll continue the discussion from the last period where we talk about acid, okay? So we talk about the Ka, which is the acid equilibrium constant, okay? And usually for an acid that dissociates into hydronium ion and its conjugated base, we can write out an expression like this. Okay, and I know in the last period, several of you have questioned on how come this term, the water term, will go to 1, right? So how come the solid and the liquid, when we write a equilibrium expression, they goes away, they equal to 1, okay? So if we think about the amount of water in a typical solution system, the amount of water is much larger than the acid or base that you add in, right? So if we calculate the molarity of water, we know usually we talk about molarity, it's mole per liter, right? So for 1 liter of water, we can say it's approximately 1 kilogram, assuming the density is 1, right? And then if we divide it by molecular weight of water, okay, then we will get 55.5 molar, and that's the molarity of pure water. Does this calculation make sense? So usually we're dealing with concentration that is less than 1 molar, okay? So in comparison, the amount of water doesn't change in this equilibrium. So when we are talking about equilibrium, we're looking at the very small change, okay? So that's one type of explanation, and it's okay that you don't understand it because there's another way to explain this. Okay, so another way to look at this equation is that because we're talking about ions, we're talking about things that they can move freely. So when we have a liquid, when we're talking about equilibrium constant, we always compare to a standard state. So standard state in this case, if we're talking about gas, is about 1 atmosphere or 1 bar. Okay, these two units are about the same. If we're talking about liquid or solid, their density remain the same. Okay, before and after reaction. So they don't really change. So that's why the activity, you can think about the exponent, their exponent will be 0. They have 0 activity. They have 0 influence on your equilibrium. Therefore, any liquid or solid, as long as it's heterogeneous, which means it's not in the same phase with the reagent that you're looking at, that will go to 1 for this simplification. So in physical chemistry or in the analytical chemistry, when we're dealing with systems that are extremely concentrated or system that is extremely complicated, then we will deal with the presence of all components in the system. That makes sense? All right, so this is a simple expression of Ka. And just to put that into perspective, we know strong acid dissociate completely in water, correct? So we all learned that in high school. Okay, so let's say what is pH 1 means. Everybody know how to calculate concentration of hydronium ion with the pH value? So pH, this little p, stand for negative log, okay? So if you want to find the concentration of hydronium ion, you can simply plug in this equation and figure it out, the hydronium, okay? So for strong acid, they dissociate completely. So that means pH 1, that is a 0.1 molar strong acid. I'll give you one example, hydrochloric acid or nitric acid, okay? So is it possible that you have pH below than 1? Is it possible? Yes, right? So think about A 0.3 molar solution, if you plug it in, you can type in your calculator if you want, you will get a number smaller than 1. Okay, so let's think about concentrated hydrochloric acid when you buy it from a store, or I guess you can't buy it from a store, you buy it from a chemical supplier. For a concentrated HCl, typically you can buy it 36 weight percent, a solution, okay? So if you do the math, it's approximately 12.1 molar, okay? So mole per liter of HCl in that solution. So this is very, very acidic, right? So you can dilute it to 0.1 molar, and we can do the simple calculation, right? Okay, the molarity, okay, times volume, and you can make a simple dilution, okay? And then the pH is depending on the concentration of your strong acid. Okay, so this is the case where we get complete dissociation. Okay, let's go back to Ka. Why is it so important? Okay, because weak acid, they do not dissociate completely. A really good example is vinegar, acetic acid. Okay, vinegar, they do not dissociate completely. We'll get a Ka value for this compound. For any compound with COOH, these are weak acid. And the acidic strength is dependent on the substituent, and we'll go more in detail in the next lecture, okay? So you can do simple math if Ka is given, right? You can do a simple math to give you what's the relative concentration, right? Because once the systems reach equilibrium, you will be able to figure it out, the number, if it's given the initial concentration or given the pH of your solutions. So you guys are expected to know how to do this calculation. There are examples in the book. Everybody know how to do this? Or if you don't remember it from high school, I suggest you guys do a practice problem from a book and relearn how to do these calculations. So one more example. So right now with coronavirus, right, people talk about using sodium hypochlorite as the disinfectant, okay? It's supposed to kill these microbes and virus, all right? So if we look at this, the acid form, the hypochloric acid, its Ka is about 2.9 and 10 to the negative 8, okay? So this is a very small value. How small is it? So if we look at something with a Ka of 10 to the negative 5, so that approximates to about 0.3% of your HA is dissociated into hydronium and its conjugated base. But for something like Ka 10 to the negative 10, that's about 0.001% dissociation. So we go from 100% dissociation for strong acid to something in a range like this, okay? So when you see 10 to the negative 8, this is gonna be in between here. You can recognize when you have a small Ka value, a small Ka means it prefers to be on the what? The starting material, the reagent, right? When we talk about pKa, it also gives you a sense of how strong or how weak this acid or how easy it is to remove the hydrogen or remove hydrogen from such compound to form a corresponding hydronium ion. Or you can use this base to pick up this proton, okay? It really depends on which definitions of acid and base you're talking about. Is it Bronsted-Lowry acid base or Arrhenius acid base, okay? Let's move on with one example. Okay, now I want you to actually calculate the Ka value given these information. Go. So how many of you get this order of magnitude? Raise your hand. We'll start talking about this problem. All right, so we know pH tells you the amount of hydronium ion is present at equilibrium, right? So you dissolve your compound in water, okay, at this concentration, okay? So this concentration is your initial concentration of HA in this equation, okay? So by using this equation, okay, you have to know how to process a pH value and get the hydronium ion concentration from pH. pH, P is negative log, okay? Just to put these fractions, point something, into a whole number, okay? To just make it look prettier. That's all it does, okay? Because you don't want to tell someone, I have a hydronium ion concentration of 10 to the negative something, right? It doesn't make any sense. When we talk about pH, we know if it's pH below than 7, it's acidic, okay? When you have a smaller number, that means it's more acidic, okay? So by doing this operation, okay, and then you can get this value. Then you simply plug in the information. We know when the acids associate, it will form its conjugated base, okay? So the concentration will equal to each other. Then you plug it into the equation and give you a Ka value. And then we can also do a check, okay? We look at the structure. It looks like it's going to be a weak acid. We look at our value. Does that look like a weak acid, right? So keep in mind, knowing by looking at the structure and being able to guess, is it a weak acid or strong acid, is something you need to learn for this chapter. If you go to your book, page 797, you will see a list of acid, okay? And so going back to example of vinegar, the acetic acid, it has the order of 10 to the negative 5, okay? So you can approximate how much acid or how much hydronium ion you have in the system. Is about 10 to the negative 3, okay? So that means not very much, okay? So that it's about, for something 10 to the negative 5, for 1 molar acetic acid, that means about 0.42% of acetic acid that you add into the system dissociated. By looking at the order of magnitude, that means for 1,000 molecules of acetic acid that is present in solution, there's only 4 of them dissociated into hydronium ion and conjugated base. That all make sense? Okay, so by looking at this table 18.3, if you don't have your book, write it down on your notebook. You can see there have different strengths. So when the Ka increased by an order of magnitude, what I mean by an order of magnitude, this is called order of magnitude. Negative 4 is an order of magnitude above 10 to the negative 5. That makes sense? Okay, so now we finished the discussion of acid, but if we can look at the backward for something going this way, you can rewrite the rate expression, okay? So let's look at a weak base. It's going to what? What it's going to do? It's going to pick up a proton, right, or accept a hydronium ion, right, from the water or from an acid, and then you form hydroxide after this reaction. Okay, so we can write an expression for Kb. Okay, and we don't need to put the liquid term in it. If we were looking at this equation, we should be able to figure it out. If you look at your page 821, if we put these two equations together, so we know from the previous chapter, when we have multiple equilibrium, we can simply times the constant together. So that's how we get Kw equal to Ka times Kb. So when we're talking about aqueous solution, If we know how much hydronium ion we have, we can figure out how much hydroxide ion that we will have. For acidic solution, that means you have more hydronium than the hydroxide. Okay, that makes sense? So from these calculations, you should be able to figure out what the relative concentration of each two by using this simple equation. So moving a step forward, pH. So we're talking about pH scale of 14, right? We can calculate amount of hydroxide by using such equation. You can connect these pH and then the concentration with this log operation, right? So you can simply calculate all of these values. Okay, when we see expressions, for example, look at ammonia in water, okay? We can immediately recognize which one is base, which one is acid, because we have pre-existing knowledge that ammonia is a weak base, right? But if we don't know, if you see, for example, the previous table I pointed at, if you see something, some compound that you do not recognize, how do we figure this out? A simple way is to see which substance has an increased number of hydrogen, which substance has an decreased number of hydrogen. Then you can recognize where did the proton go, okay? So proton, hydrogen, they're the same thing in this description. So here, you have base. Then in this case, water acts like an acid. So base always form conjugated acid, okay? Because in this form, for example, when I have ammonium hydroxide solution, it's a great proton source, because if we have something stronger, is something that's a stronger base, right? It's gonna immediately take this hydrogen from the ammonium and regenerate this compound, okay? So when we're talking about the strength of acid and base, it's all relative. So you should be able to recognize this is the acid's conjugated base. So let's look at another example. So I simply just change oxygen to sulfur. So this is still valid, but except the strength of H2S is going to be different than water. So we can look at, there's a chart that talks about the relative strength on page A06. So if you go to the A06, you will see a list that describe what are strong acid, okay, and what are strong base. And by looking at this chart, there are some conjugate base or conjugate acid that doesn't matter, okay? They're negligible, because when they are present in water, their Ka value prevent them from taking additional hydrogen. For example, when we dissolve sodium chloride into water, we do not get HCl. That makes sense? Because chlorine doesn't really want another hydrogen. It's happy to be solvated by a water molecule. So now we're going to talk about these three are strong acids. So when we dissolve in water, it immediately dissociate, okay? So when we dissolve 0.1 molar, ideally, they're going to give you a pH of 1. Okay, we can measure that with a pH meter or some acid-base indicator that can indicate the extent of dissociation, which tell you the pH of the solution. So how do we figure out which one is stronger and which one is weaker relatively? One way is to dissolve into another solvent, for example, acetic acid, okay? So that means the ability of these things to dissociate in acetic acid will tell you which one is stronger, which one is weaker. So how many of you think HCl is the strongest? HBr? HI? Talk with your peer to explain why Hi might be the strongest acid. So if we look at periodic table, how many of you get the answer? As we go down the table, these ions become bigger, right? So that means your bond length becomes what? When the ion's bigger, what about the bond length? The distance between your two atoms, H and Cl or H and I, become bigger, right? As you go down the periodic table, okay? Or we can also look at bond dissociation energy of relative strengths of these three bonds. If you go to page 816 and it tells you the answer, we can look at it by both bond length and bond energy. Okay, and you see there's a dramatic difference. So going back to talking about acetic acid and other weak acid, that's why I mentioned the identity of this group or the neighboring group will have an effect, because a relative acid strength is dependent on how well you can hold on to the hydrogen or the proton, or how willing you are to give off that hydrogen or proton. So that is the key when we are talking about acid and base. And they're all relative. When you have strong base present, it's going to immediately take more hydrogen from your system. But when you have such a weaker base, it's going to take less hydrogen or less proton from the system. Make sense? Okay, and I think that's all I have for today. And I know in the last lecture, I asked you guys for some feedback in terms of what you guys don't understand. And I know you guys asked very good questions on these, and then I will talk about the answer. Remember in the last period, I talked about Kc and Kp. So that means equilibrium constant in terms of concentration and equilibrium constant in terms of pressure. I give you this equation, PV equal to nRT, which you guys learned last semester. So I will go through a derivation of how do we get the exponent delta n that track the change in the mole of gas, okay? I know the way we structure this class is we will talk about thermodynamics later, but I find it very difficult to explain why without knowing a little bit of thermodynamics. But for this problem, you don't really have to worry about thermodynamics. It's just a simple mathematical manipulation of such equation. So if you go back and read the chapter 18 this weekend, you will understand it more. But I'll go through the derivation very quickly. So from this equation, okay, we know this is just what we need to do when we calculate equilibrium constant. When we talk about Q, at equilibrium, Q is equal to your K. That makes sense? This is different than rate law because this is completely two different concepts. Rate law is a way to describe how fast a reaction is happening, okay? How fast your reagents are being consumed. But for equilibrium constant, we care about after infinite amount of time, how much is left, okay? What kind of component you have in your system. So for Kc, we can simply follow the rule, okay? By rearranging PV equal to nRT, we can just move things around, okay? We can move this term over here, move this term over here, you get a rearranged equation. And now is where you have to be very patient. Do not lose your indicator of what this pressure corresponds to. All right, so when we're talking about the concentration term, right? This is reaction quotient, so we simply put the factor based on the stoichiometry. We put the exponent, okay? Here's 2, and it's always product over reactant, okay? So we know concentration is how many molecule in a fixed space, right? So therefore, these two will be equivalent to each other, right? So since this is a square term, everything is squared, all right? So based on mv equal to p over RT, we can get this equation. Okay, then we can simplify this equation by times this term, this is 1, right? But it helps you to cancel out the term. Okay, so in the end, you will get, any question? This RT comes over here. So if we look at the way we set up our QP, when we're talking about pressure, it's exactly the same way we describe it. And that's why we can substitute in QP over here. And RT, okay? So this satisfies this equation here. We simply move the term around, okay? The QC is over there. We divide RT from the both sides, and then we end up with this equation. And this is delta N, which describes, this comes from, in the end, you end up with 2 molecules. When you have because this is really hard to decide what the molecularity if you do not know the mechanism. But the way you can look at it, it can be a termolecular reaction, okay? That means all 3 of them have to collide into each other at the right position, at the right speed, because the speed is determined by its energy for the reaction to happen. But normally, most reactions are bimolecular, okay? So it's likely a 1 NO collided with O2 and form an intermediate. So you've probably seen it before. It probably formed a NO3 or NO, depending on what your reaction product is, okay? Okay, so going back to where this -1 come from, this is the number of product that is formed minus the total number that you have, okay? It's always final minus initial, okay? So this is where this -1 come from, get it? So you can simply, let's say we can change to a different molecule, right? This doesn't have to be NO, it doesn't have to be O2. It can be A, B, C, right? You can change the term here and go through your math. You will get this equation, okay? This is a generalized equation. That all makes sense? Okay, and I know for the 1-minute paper, there are some students who asked this question. I saw some very smart answer to proving where this delta N come from by using M or N. So you can do the same manipulation, okay? And then you go through the math, and then you will get this equation. So we previously talked about Van Hoff equation, and I know we did not spend too much time on Van Hoff equation. This is because we couldn't really discuss that term without going into thermodynamics. But what the key of Van Hoff equation is, we know by looking at the equation, it simply tells you here the K is big K, okay, the equilibrium constant. Heat of reaction is generally a constant. It's not influenced by temperature difference. So that basically means you have higher temperature, you have a faster reaction for the Arrhenius equation. But for Van Hoff equation, it's basically tell you where the equilibrium constant is going to go. In the Gibbs free energy, it has an equation that correlate the Gibbs free energies of your reaction system and how it's related to equilibrium constant, okay? And we know delta G is delta H minus delta S, okay? So what you can do is at different temperature, you plug in the equation, okay? Then in the end, you will get this expression because this T times delta S term cancel out with each other, okay? The delta S is also at the standard condition. It's not really influenced by the reaction temperature, okay? So in the end, you can get this equation. If you ask me what is it really for, this is for you to calculate what your equilibrium constant would be at different temperature. Then you can do the similar plot to Arrhenius equation. You plot it 1 minus T because we can measure how much product is formed for a reaction and determine your equilibrium constant, right? And if we plot the equilibrium constant as a function of a time, sometimes you will get a plot like this. sometimes you will get a plot like this. Okay? Why? Because the slope, if we look at the mathematical expression, so this is natural log K here. If we look at this expression, when we plot a thing like this, a slope is going to give us this minus delta heat of reaction over R term. So for the endothermic, we have a positive heat of reaction. Because you have a negative sign, you will get a negative slope. Okay, so that makes sense because this is the inverse of temperature, so everything is opposite. So for endothermic, it needs heat for the reaction, so when you add more heat at higher temperature, it happens more easily. Okay, so it's going to shift to the product. For an exothermic system, it releases heat, so when you're adding more heat, it's going to shift the equilibrium backward. So that's what Van Hoff equation is all about. And I know you probably never seen this equation before. We'll talk about the derivation of it when we get to that chapter. But this is where this equation comes from. I mean, the reason why I did not spend too much time on it is I see its similarity to Arrhenius equation. So for Arrhenius equation, only this term, it goes from, the difference is this term, okay? And in the Arrhenius equation, it's T1 minus T2. And that has to do with this term, okay? All right, so I think that's all I have for today.